Calc BC students, we are taking a look at our third and final example from number 2, finding the radius of convergence. It's possible that you've seen the first two videos, parts A and part B. It probably seems to be the case. If you've done that, then this would most likely adhere to the third criteria of how a particular power series may be centered, as indicated in theorem 9.20 up above. But let's go ahead and not assume anything and jump right into the example and take care of what's in front of us here. First of all, we still must make the determination, potentially, where is this particular series centered? And it's usually not difficult if you can find the x. And of course, the x located right up here in the numerator doesn't have any other kind of grouping symbols around him to give us the idea that we might be centered somewhere other than 0. So we know that we're probably safe to say that we are centered at 0. Okay, and we'll change the pen here a little bit. Now, if you recall from the other examples, I find it really useful to develop this secondary function that I'll call u sub n, that really just takes on the exact value that you've got of your particular nth term expression here. Because what we have discovered is that we have a very handy test that will help us determine whether or not we've got this convergence anywhere else other than where it is centered. And that particular test, called the ratio test, which says to take the limit as n approaches infinity of the absolute value of your u sub n plus 1 term divided by your u sub n. So in this particular instance, any n's that we see up here, we're going to replace them with an n plus 1. So we would have negative 1 to the n plus 1 multiplied by 2, getting a little bit ahead of myself, multiplied by x. How about that? There we go. X raised to the 2, and we're going to replace this n with an n plus 1. I'll simplify it a little bit later. No sense in getting ahead of ourselves. And then the denominator here would be a 2 multiplied by an n plus 1, all plus 1, and then we still have to take that quantity to a factorial. And then we'll divide all of this by the original nth term expression, negative 1 to the n times x to the 2n plus 1, all over 2n plus 1 factorial. And it's important that we note that we're only concerned about the positive value of this, so we would still have our absolute values around it. And yes, that is one hideous looking fraction, isn't it? And one other little thing here, kind of important, that limit statement should still be written right here. I get on my students all the time for forgetting to write that, so I don't want to do that. And for that very reason, I'm going to start off with that limit statement here. Now all we're going to do is perhaps take care of our n plus 1s and maybe do as much reducing and simplifying as we can in that regard. And at the same time, if you follow along, I'm going to go ahead and multiply by the reciprocal of the denominator. So what I would have here in the absolute value signs would be negative 1 to the n plus 1 times x to what would end up being the 2n plus 2 plus 1, or 2n plus 3 power. And it would still all be divided by 2n plus 2 plus 1, or 2n plus 3 factorial. And then, as I said, I would go ahead and multiply by the reciprocal, which would give me a 2n plus 1 factorial in the numerator on top of a negative 1 to the n times x to the 2n plus 1. And now we ask ourselves, what are we going to do with this? What kind of simplifying can we perform with this particular expression? Well, first of all, I think we could do some of the obvious things. And by that, I mean some simple cancellations of the fact that negative 1 to whatever power could produce a -1 result, it could produce a +1 result, but does it really make any difference? Because we're talking about something that's inside of absolute values. So it's going to be a +1 no matter what. And the same can be said for this guy down here. So essentially you can just ignore those two things. And then as far as the x exponents here, the 2n plus 3 with the 2n plus 1, you might recall that the power rule says, let's switch back to my darker green here. We recall that we had a theorem from algebra, that says that we can subtract those two exponents. And if we do, 2n plus 3 minus the quantity 2n plus 1 would leave us with an x squared, and that would be on top. Now, as far as the 2n plus 1 factorial over 2n plus 3 factorial, if you think about what's happening with this particular expression, 2n plus 1 factorial. Say we plug in various values for this n. Right, let's say if we're taking a look, and in fact, let me change that up. Let's look at 2n plus 3 factorial. Let's see if we can get to understand it from this standpoint. If we were to let n equal, say, 0, great place to start. We obviously start with the value 3. And then if we were to let n be 1, we notice that we move up to our next term, which would be 2 plus 3, or 5. And if we let n be 2, we're up to 7, etc., 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 until we ultimately obtain the 2n plus 3 as our final term. Well, what's important to understand is really what the term would be just prior to this 2n plus 3. And where some students might make the mistake and think, well, wouldn't it just be the very first, say, integer value that would come before that final result, or in this case 2n plus 2, and that's not really correct. Because we are talking about odd values only that we are multiplying together, this would really be a 2n plus 1 that would be in the parentheses there. Now, in this particular example, if a student were to make the mistake and think that both 2n plus 1 times 2n plus 2 would be the result, it wouldn't necessarily throw your final answer off, as you're going to see in a little bit. But if you want the algebra to be correct, then you really only want to come to the realization that you'll be left with 2n plus 3, is what I meant to say, as the leftover value here, not 2n plus 3 times 2n plus 2, if that makes any sense. Okay, now, in this particular situation, we are going to go ahead and complete our limit problem, and we can essentially let our n value take on an infinite value. 2 times infinity plus 3, of course, is going to make this denominator very, very large. So you have x squared over essentially what is to be infinity, which is going to really rule out any possibility for the numerator to take on some value that's going to be significant. No matter what x that you seem to plug in, you're going to get a 0 for this particular limit. So this limit is going to equal 0. Now, if you recall, the ratio test has a relationship sort of built in to its results being either bigger than 1 or less than 1. And since 0 is less than 1, we would then conclude that our series converges for all x. Not just the original x where it was centered at, 0, but for every single x to the left, every single x to the right. This limit, this series, if we were to add it all together, would approach some nice finite term ultimately. So if we do have a convergence that shows for all values of x, the way that we would want to address it in this particular example is by stating the radius. Right? We're not so concerned with the interval of convergence in this example. That'll come with some later videos. So our radius, our capital R, is ultimately infinitely large, so we'll just call it R equal infinity. And now, as you can see from examples 2, parts A, parts B, and part C, all three of the different possibilities that one could see as the result of examining a power series do come to be true. Thanks, and we'll see you next time.